Welcome to our deep dive today. We're going to be looking at a pretty interesting paper. It's called Ringworlds and Dyson Spheres Can Be Stable. And it's all about, well, the physics of these, hypothetical megastructures. And you've given me some research to sort of try to unpack it all.
Yeah, the paper uses the framework of the restricted three-body problem from celestial mechanics to explore the stability of ring worlds and Dyson spheres.
Okay, so for those maybe who aren't familiar with that, can you explain what the restricted three-body problem is?
Sure. The restricted three-body problem is a classic problem in astrophysics, where we examine the motion of a small object, like a satellite, under the gravitational influence of two much larger objects, like a star and a planet. And so this paper applies this model to hypothetical megastructures. So basically, the small object is not a satellite, but a giant ring, or a vast shell.
I see. So instead of like a tiny satellite orbiting a planet, we're imagining like a massive ring or sphere interacting with stars. Now, the paper starts by discussing James Clerk Maxwell's work on Saturn's rings. Can you remind us what his findings were and why they're relevant here?
So back in 1859, Maxwell demonstrated that a solid ring around a single mass, like Saturn's rings, is inherently unstable. Any slight disturbance, and it would eventually collapse onto the central object. So this is really crucial to our discussion because it raises the question, if Saturn's rings are unstable, could ring worlds, these massive hypothetical structures, ever exist in a stable configuration?
That's a good point. So how does this paper kind of address that question?
Well, the paper explores the stability of ring worlds and Dyson spheres within a binary star system. So that's a system with two stars orbiting each other. And this is where things get really interesting. The paper demonstrates that both rings and shells can achieve stability under certain conditions in a binary system.
Fascinating. So the presence of a second star kind of fundamentally changes the dynamics.
Precisely. But it's not as simple as just having two stars. There are very specific conditions that need to be met for these structures to be stable.
Okay, let's dive into those conditions then. What makes a ring world or a Dyson sphere stable in a binary star system?
Well, the paper outlines three key conditions. First, the ring or shell must enclose the smaller of the two stars in the binary system.
So the megastructure has to be built around the less massive star.
Yes. Second, the mass ratio between the two stars must be below a specific threshold. In other words, the smaller star needs to be significantly less massive than the larger one.
Sounds like a delicate balancing act. What's the third condition?
The third condition relates to the radius of the ring world. If it's too small, it becomes unstable, just like Maxwell's ring. But if it's too large, it also loses stability. There's a sort of sweet spot where the gravitational forces reach an equilibrium.
That makes sense. It's all about finding that gravitational sweet spot where the ring world can remain stable. Now, the paper uses the terms L6 and L7 to describe specific locations in a binary system where these stable points exist. Can you elaborate on what those points represent?
Sure. Imagine a line connecting the two stars in a binary system. The L6 and L7 points lie along this line, but are closer to the smaller star. These points are not directly centered on the smaller star. They're offset, creating a specific region where the gravitational forces allow for the stability of a ring world or Dyson sphere.
So these points, L6 and L7, represent those gravitational sweet spots we were talking about.
Exactly. And the paper provides detailed figures and calculations to illustrate the precise locations and conditions for stability at these points, which we can discuss further.
That sounds like a perfect segue into the next part of our discussion.
Yeah.
But before we get there, I'd like to touch on Dyson spheres specifically. How does the stability of a Dyson sphere around a single star compare to its stability in a binary system?
That's an important distinction. The paper demonstrates that a single Dyson sphere around a single star would be marginally unstable. Any slight perturbation would cause it to drift and eventually collide with the star. However, in a binary system, if a Dyson sphere encloses the smaller star and the mass ratio is below the critical value, it can achieve stability at those L6 and L7 points.
So a binary system offers a more stable environment for these hypothetical megastructures.
Precisely. And to further illustrate this, the paper uses our own Sun-Saturn system as an example.
How does the Sun-Saturn system relate to the stability of megastructures? Saturn is much smaller than the Sun, isn't it?
Yes, but their mass ratio is still within the range where ring stability is theoretically possible, according to the paper's calculations. Even with this small mass ratio, there exists a specific range of ring radii around Saturn where stability is achievable.
That's fascinating. So even our own solar system, in a way, hints at the possibility of stable megastructures.
Hmm.
It seems like this paper really expands our understanding of these concepts by moving from single-star systems to binary systems.
It certainly does. By shifting our focus to binary systems, the paper opens up a whole new realm of possibilities for stable megastructures.
And that shift in perspective has some intriguing implications, especially when we start talking about the search for extraterrestrial intelligence.
That's right. The possibility of stable megastructures in binary systems could have significant implications for our search for extraterrestrial intelligence, or SETI.
Let's delve into that. How does this research change our perspective on SETI?
Well, it suggests that instead of focusing primarily on single-star systems, we should prioritize binary systems with specific characteristics when searching for evidence of advanced civilizations.
Specifically, binary systems with a mass ratio below the critical threshold for ring and shell stability as outlined in the paper.
Precisely. These systems offer the most promising environments for the existence of stable megastructures, which could be potential indicators of advanced extraterrestrial civilizations.
So we're looking for systems where the smaller star is significantly less massive than its companion. That narrows down our search considerably.
Indeed. And the type of technosignatures we would look for would depend on the specific megastructure we're considering, whether it's a ring world or a Dyson sphere.
Okay, let's break that down. Starting with Dyson spheres, what kind of observational evidence might suggest their presence in a binary system?
A Dyson sphere, by its very nature, would capture a significant portion of a star's energy output. This captured energy would be re-emitted as waste heat, primarily in the infrared portion of the electromagnetic spectrum.
So we'd be looking for stars that are unusually bright in infrared.
Yes, but it's crucial to remember that we're focusing on binary systems. So we'd be looking for a binary system where one star shows an unexpectedly high infrared excess, and the system has the right mass ratio for a stable Dyson sphere around the smaller star.
That makes sense. It helps us filter out other possible explanations for infrared excesses. Now, what about ring worlds? What kind of technosignatures would we look for in that case?
Detecting ring worlds would be more challenging. Unlike Dyson spheres, which completely enclose a star, ring worlds only partially utilize a star's energy. They don't create the same kind of massive infrared excess.
So how could we possibly detect them?
It would require extremely precise observations. One potential method would be to look for periodic dips in a star's light as a ring world passes in front of it.
Similar to the transit method used to detect exoplanets.
Yes, but significantly more challenging due to the size and potential orientation of a ring world. We might also look for variations in a star's radial velocity caused by the gravitational pull of a massive ring world.
So it's like searching for subtle wobbles in a star's motion.
Precisely. However, both these techniques would push the limits of our current observational capabilities. Detecting ring worlds would require advancements in telescope technology and data analysis.
It seems like finding evidence of ring worlds would be a monumental task. But let's shift our focus back to the specifics of these stable regions for megastructures and binary systems. You mentioned that the paper provides detailed figures and calculations to illustrate this. Can you walk us through some of those visuals?
Certainly. Let's start with Figure 7, which focuses on the stability of rings at the L6 point in a binary system. This figure presents a stability map with the mass ratio of the stars on one axis and the ring's radius on the other.
And the shaded area on this map represents the combinations of mass ratio and ring radius where the ring can be stable.
Yes. What's striking about this map is that the stable region is a surprisingly narrow band. It highlights the delicate balance required for a ring world to maintain stability in a binary system.
So what are some key takeaways from this stability map?
One key takeaway is that stability is only possible when the mass ratio is quite small, specifically less than about 0.00044. This means the smaller star must be significantly less massive than the larger one for a ring world to be stable around it.
So the smaller the secondary star, the more likely a ring world could exist around it.
In a way, yes. As the mass ratio decreases, getting closer to zero, the range of possible stable ring radii expands. But there is still an upper limit to how large a stable ring world can be, even in the most ideal scenario.
What about the L7 point? Does it offer similar possibilities for ring world stability?
Unfortunately, no. The paper's analysis shows that the L7 point is inherently unstable for rings, regardless of the mass ratio or ring radius.
So only one side of the smaller star offers a potential region for stable ring worlds. That's an interesting asymmetry.
Indeed. It further emphasizes the unique and delicate gravitational dynamics at play in binary systems.
Now let's move on to Dyson spheres. Figure 13 in the paper illustrates the stability of a shell, representing a Dyson sphere, enclosing the smaller star in a binary system. Can you explain what we see in this figure?
This figure demonstrates that the mass ratio is again the critical factor for stability. For a Dyson sphere to be stable, the mass ratio between the stars must be below a specific value, which in this case is 19. This means the smaller star's mass cannot exceed 1/9 the mass of the larger star.
And if the mass ratio exceeds that threshold?
The figure shows that if the mass ratio is too high, the Dyson sphere becomes unstable. The analysis reveals a pair of real eigenvalues, indicating a tendency for the sphere to drift and eventually collide with the star.
Interesting. And this stability, or lack thereof, is independent of the Dyson sphere's radius. That seems different from Ringworlds, where the radius played a crucial role.
That's an astute observation. The difference stems from Newton's shell theorem. This theorem states that a spherical shell's gravitational interaction with an object inside it is zero, regardless of the object's position within the shell. So the sphere's radius doesn't affect its stability around the enclosed star.
I see. It's as if the enclosed star doesn't gravitationally see the shell surrounding it.
Yes, that's a good way to think about it. Now, while this paper primarily focuses on the stability of megastructures in binary systems, it also makes a fascinating connection back to Maxwell's findings on ring instability.
That's right. Maxwell showed that a ring around a single mass is inherently unstable. But this paper demonstrates that rings can be stable in a binary system, specifically at the L6 point under the right conditions. It's a remarkable extension of Maxwell's work.
Indeed. And the paper provides a concrete example using our own Sun-Saturn system to illustrate this point. Figure 14 shows the eigenvalues for a hypothetical ring around Saturn.
Even though Saturn's mass is minuscule compared to the Sun.
Precisely. Even with that small mass ratio, the figure demonstrates that a ring around Saturn could be stable if its radius falls within a specific range. This range is expressed in non-dimensional units relative to the distance between the Sun and Saturn, and translates to a ring extending hundreds of millions of kilometers.
That's incredible. It really highlights the vast scales we're dealing with when discussing megastructures. And it reinforces how this paper broadens our understanding of ring stability, moving from single-star systems to binary systems.
It certainly does. By shifting our focus to binary systems, this paper unlocks a new realm of possibilities for stable megastructures. It's a shift in perspective that challenges our preconceived notions about what's possible in the cosmos.
And it leads us to contemplate the immense engineering challenges involved in constructing such colossal structures.
Indeed. The material science considerations alone are mind-boggling.
Let's explore that aspect in our next segment. What kind of materials could withstand the stresses and strains of building a ring world or a Dyson sphere? What advancements in materials science would be needed to make these concepts a reality? So we've been talking about, the sheer scale of ring worlds and Dyson spheres. It's kind of awe-inspiring, but it also makes you think, how would you even build these things? What kind of materials could withstand that much stress and strain, to build these massive structures?
Yeah, that's a crucial consideration. The material science challenges associated with these megastructures are immense. I mean, we're talking about structures that, dwarf planets, requiring materials with exceptional strength-to-weight ratios, and the ability to withstand extreme temperatures, gravitational forces, you name it.
Yeah, it's hard to even imagine what kind of material you would use, to even start a project like that. Does the paper offer any insights into potential materials or even construction techniques?
Well, the paper touches upon the potential of advanced materials, like graphene, for instance. Graphene is an allotrope of carbon with a two-dimensional hexagonal lattice structure. It's known for its incredible strength and lightweight properties. It's often touted as a potential wonder material for various future technologies, and megastructures are no exception.
Yeah, graphene's strength and lightness definitely make it a contender, at least in theory.
Yeah.
Are there any other materials or concepts even that might be relevant to megastructure construction?
Yeah, the paper also briefly mentions smart materials, materials that can adapt to stress and potentially self-heal. Imagine a material that could detect a weak point, say, in a Dyson sphere, and automatically reinforce it before a catastrophic failure. Such advancements in material science would be absolutely essential for making these, megastructures a reality.
Smart materials. that can like self-repair or adjust their properties
Yeah.
in response to external forces. That sounds like something straight out of, science fiction.
It does sound futuristic, but research into smart materials is a rapidly developing field with potential applications across, various industries. And while we're still far from creating materials capable of withstanding the demands of a megastructure, the concept itself highlights the kind of, innovative thinking that is required to overcome these immense engineering challenges.
It seems like the construction of ring worlds or Dyson spheres would require like a paradigm shift, really, in our understanding of materials and engineering principles.
Absolutely. It would necessitate advancements not only in materials science, but also in areas like robotics,
Hmm.
automation, large-scale construction techniques. It would be a feat of engineering, really unparalleled in human history.
But even if we could,
Mhm.
like, overcome these technological hurdles, the scale of resources required for a project like that, it'd be staggering.
Undoubtedly. Constructing a megastructure would require an unimaginable amount of raw materials, energy, and time. It's a project that would likely take centuries, if not millennia, to complete, requiring the coordinated efforts of a civilization far more advanced than our own.
That's a humbling thought.
Yeah.
This paper has taken us on quite a journey from the theoretical physics of megastructures to the potential implications for SETI and the immense challenges of their construction. So as we wrap up our deep dive here, what are some key takeaways that you'd like our listeners to reflect on?
Well, first and foremost, this paper challenges our assumptions about the feasibility of megastructures by demonstrating the potential stability of ring worlds and Dyson spheres in binary star systems. It expands our understanding of celestial mechanics and opens up new possibilities for the existence of advanced extraterrestrial civilizations.
Yeah, it's a reminder that our universe is full of surprises and that our current understanding of what's possible may be limited.
Precisely. And second, this research underscores the interconnectedness of seemingly disparate fields, like astrophysics, material science, and SETI. The search for megastructures requires a holistic approach, integrating knowledge from various disciplines to push the boundaries of scientific inquiry.
It highlights the importance of interdisciplinary collaboration and the potential for, unexpected discoveries when we challenge conventional thinking.
Exactly. And finally, this paper serves as a call to action, really, for the scientific community. It encourages us to refine our search strategies for technosignatures, to
Yeah.
prioritize the study of binary star systems, and invest in the development of advanced technologies that could one day, make the construction of megastructures a reality.
It's an invitation to embrace the vastness of the unknown and continue our exploration of the cosmos with a renewed sense of wonder and determination.
Indeed. The search for megastructures is a testament to the boundless curiosity and ingenuity of humankind. It's a journey that may take centuries, but the potential rewards are immeasurable.
Well, on that note of cosmic ambition, we conclude our deep dive into the fascinating world of ring worlds and Dyson spheres. We hope this exploration has sparked your imagination and left you with a deeper appreciation for the endless possibilities that await us in the vast expanse of the universe.
Thank you for joining us on this journey. May your curiosity continue to guide you as we venture further into the mysteries of the cosmos.